If you want to understand the world, you have to understand change. A swinging pendulum, the volume of a sound, the shaking of an earthquake. To visualize this mathematically, we use a simple graph. Time marches forward relentlessly along the horizontal axis. As time passes, the quantity we are measuring fluctuates up and down along the vertical axis. Imagine a seismograph needle resting on a moving roll of paper, leaving a permanent inked trail of its changing state over time. Some changes in nature repeat perfectly over time. We call this periodic motion. The most fundamental physical model we have for a perfectly repeating pattern is uniform circular motion. Imagine a glowing car on a Ferris wheel, viewed from the front. As the wheel turns at a steady, unchanging speed, known as angular velocity, the car travels in a perfect circle. It traces the exact same path over and over, an unending cycle governed by the simple geometry of a circle. How do we translate this circular motion into a graph of time? By tracking just one dimension at a time. If we attach a laser pointer to our spinning wheel and project it onto a wall that moves horizontally like a conveyor belt, what happens? By tracing only the vertical height of the spinning point as time moves forward, we draw a perfectly smooth, undulating S-curve. This mathematical snake-like curve is the sine wave, a simple circle unrolled across time. Every simple wave is defined by two key properties. Think of ocean waves crashing on a beach. First is amplitude. This is the sheer physical height of the wave. Are we dealing with a massive, towering tsunami or a gentle ankle-high ripple? The second is frequency. This measures how rapidly the waves arrive. Does a wave hit the shore once every 10 seconds, like a long, lazy swell? Or are they tightly packed together, hitting rapidly 2 or 3 times a second? Amplitude is height. Frequency is speed of repetition. But the real world isn't made of perfectly pure single waves. What happens when multiple waves overlap? Imagine dropping a large rock and a small pebble into a calm pond simultaneously. Their expanding ripples collide and interfere. Mathematically, their heights simply add together at every single point in time. Where two crests meet, they create a super tall water peak. Where a crest meets a trough, they cancel each other out, leaving flat water. This process, called superposition, takes simple ingredients and bakes them into highly complex, jagged, messy signals. If adding waves together makes a complex signal, can we run the process in reverse? This is the central, profound realization of wave mechanics. Any complex, messy signal, whether it's an earthquake vibration or a chord played on a piano, can theoretically be unbaked. Imagine a magical culinary centrifuge. You pour in a blended mixed berry smoothie, the complex signal. It spins and unblends the mixture, producing separate, perfect piles of intact whole fruit. One pile of strawberries, one of blueberries, and one of raspberries. Messy signals hide pure waves inside them. This unblending process is achieved using a masterful mathematical tool, the Fourier transform. Think of it as a mathematical glass prism. Just as a prism shatters white light into a rainbow of distinct colors, the Fourier transform takes a complex time signal and maps it into a completely new perspective, the frequency spectrum. By shifting our perspective by 90 degrees, time disappears. Instead, we see a bar chart, much like a digital graphic equalizer on a stereo. We instantly see exactly which pure frequencies are hiding inside the noise, and exactly how loud each one is. This elegant equation is the key to unraveling the hidden symphonies of the universe.